All right, welcome. Today we are discussing lines, tangent lines. Lines that are tangent to a circle are basically any line that hits the circle in exactly one point. So if you look at the picture to the right of the paragraph, that's an example of a tangent line. The point of tangency is the point in which the line and circle intersect. So it's going to be that guy right there. Another sort of vocab term we need to be aware of is common tangent. So a common tangent means that it is a line that is tangent to multiple circles, or it's a tangent line that the circles have in common. So when we are drawing our tangent lines, we need to make sure that the lines intersect the circles, but do not cross through them. Again, intersect, but not cross through. So if we are looking at this pair of circles and we want to know where the common tangents are, we need to draw lines that go outside the circles, but that do not pass through them. So there we go. Our points of tangency, therefore, would be here and here. And if we look at it, we can draw another one going across the bottom with points of tangency here and here. When we look at this example, right, we can again draw going across the bottom. We can again draw going across the top. But this time, since there is actually space in between the circles, we should be able to get some tangent lines that run through the middle like so. So there's one. And then the other would go like this. Just right there. There we go. All right, so again, points of tangency are where the lines and the circles intersect. A tangent line must hit the circle at exactly one point. It cannot pass through the circle. All right. When a line is tangent to a circle, it will always be perpendicular to the radius of that circle. So if we look here, the line L is tangent to circle S because there is a right angle where ST meets with line L. That right angle will always occur at the point of tangency. So if we are attempting to determine whether or not the line is tangent to the circle, all we have to do is figure out whether or not the line forms a right angle at the point of tangency. And of course we do that by proving that this is a right triangle. So we're going to use our Pythagorean theorem. Plug in what we know. And so we should get 17 for the third side of the triangle. So if JK is 17 units long, then we have the correct dimensions. Notice that they marked the 9 going along the outside of the circle. I need to find that missing piece. Right? So the radius of the circle from J to L is 8. Since the radius is the same length all the way around the circle, then there must be 8 units there. So if I'm looking for the total length of Kj, I add the two pieces to get 17. So because I got 17 for both lengths, KL is tangent to circle J. Alright, so in this example, we already know that the line is tangent to the circle. We simply need to find the missing value. So just like we were saying, if JH is tangent to circle G, then the radius makes a right angle at the point of tangency. And we know that for every right triangle, a squared plus b squared equals c squared. So now all we have to do is plug in the parts based on what we know. So we notice for the line from G to H, they did not give us the total, but instead gave it to us in parts. And so we know that since we would add the two parts to find the total, the length from G to H is going to be x plus 8 instead of a given value. So now we just solve the equation. And we need to remember that from Algebra 1, if we want to square a binomial inside the parentheses, we cannot simply distribute the two. We have to multiply what's in the parentheses with itself. So we're going to distribute whatever's in the parentheses to a second copy of the same binomial. So x times x gives me x squared. 8 times x gives me 8x. When I distribute the 8 to the x, it gives me another 8x. And then the 8 and the 8 multiply to 64. And we notice that there is an x squared on both sides of the equation, so we can subtract it out. We also notice that we can combine like terms to simplify down even further. And now we can solve the equation for x. And there we go. Alright, our next theorem is a little bit simpler. Basically, when we have two tangent lines that intersect at the same point on the outside of the circle, the two lines are congruent. So in this question here, since AB and CB are both tangent to the circle, and they both contain point B, they must be equal to each other. So AB must equal BC, which means that x plus 15 needs to equal to x minus 5. And now we solve. So of course we subtract our x and then add the 5. And we get that x equals 20. And for our final little example of the day, we know that when we circumscribe a polygon, or when we inscribe a circle into a polygon, that the circle is going to be tangent to the polygon on each of the sides. Right? So the circle hits the polygon at exactly 3 points, or hits the triangle, I should say. The question asked us to find the perimeter of the triangle, so we basically just need to be able to fill in the missing pieces so that we can find the length of each side. Well, I noticed that AD is tangent, AE is tangent, and so since they intersect at point A, they should be the same length. So if there's 8 feet from A to D, there should be 8 feet from A to E. I know that the same thing is true for BE and BF, so if there's 7 feet from B to E, there should be 7 feet from B to F. If there's 10 feet from B to C, then in order for everything to add up properly, we need 3 feet from C to F, which means there should be 3 feet from C to D, because again, we have two tangents intersecting at a point outside of the circle. So what we need now is the perimeter. Everything's filled in. All we need to do is combine all the sides. So from A to B, it looks like we have 15 feet. From A to C, we have 11 feet. And then, of course, we already knew that there was 10 feet running along the bottom from B to C. So the perimeter of our triangle is going to be 11 plus 15 plus 10. And that's all there is to it. That's all we have for today.